Good afternoon, everyone. So welcome to our channel Math Sapram. Okay. So today we are going to see fourth lecture on uniform convergence of functions. So let's start today's lecture. Okay. So we have to observe few things. Okay. So you observe first thing that note you see this function fn x is equal to e to the power minus nx square. Okay. On R. So you see that if x is equal to 0, then f and 0 is actually 1. For all n belongs to n. It means f and 0 tends to 1 because this is a function. Okay. As n tending to infinity. And if x is not equal to 0, then what is? So this is 1 upon e to the n square. That will, since x square is non-zero, so nx square tends to plus infinity, and this will tends to 1 upon infinity, that is 0. Okay. So it means f and x tends to 0 as n tending to. So what is my fx limit function, pointwise limit function? It is 1 if x is equal to 0, and it is 0 if x is not equal to 0. So we know that each fn is differentiable function. Fn converging to f pointwise. Okay. This fn is for each n is differentiable function for each n function on R. But you see that f is not differentiable because f is not even continuous. A differentiable function is always continuous. So since f is not continuous at x is equal to 0, so it is not differentiable as well. Okay. Not differentiable. So if a function of if sequence of differentiable function converges to pointwise to some function, it does not need it may not happen that limit function, pointwise limit function will also be differentiable function. Okay, we have seen this example. Okay, now you see another example. No, another observation. Note 2. So you take this function fn x is equal to x square plus 1 by n. X belongs to real number. Okay. Now, what is its pointwise limit? Pointwise limit is that is mod x. So you take fx is equal to mod x. Then you can check that fn tends to mod x. Fn tends to f in mod x function. Fn converges to f uniformly on R. So how you can check it? How you can check it? We know that we know that the under root, if we take this root x is a uniformly continuous function. Continuous function on R. Okay. So we can take we can dissolve R in the following form. So I can take two sets, x belongs to R, such that mod of x is less than equal to 1, union x belongs to R, mod of x is greater than 1. Okay. Now, root x is uniformly continuous on this interval. 0 to infinity. Okay. So now you take this interval, x belongs to R, such that mod x is less than equal to 1. That is nothing but this interval. So gx is under root x uniformly continuous on this interval. Okay. This interval. Now, what can I do? I can do one thing. Uniformly continuous, let epsilon greater than 0 I am taking. Okay. So I can fix let epsilon greater than 0. Then by definition of uniform continuity, we have that under root x minus under root y is less than epsilon. We have, so there exists delta greater than 0. We have this one for all xy belongs to minus 1 to 1, such that x minus y less than delta. Okay. But by Archimedean property of real numbers, we have there exists natural number n belongs to n naught belongs to n, such that 1 upon n naught is less than delta. Okay. 1 upon n less than delta. So I can take my y is equal to x plus 1 upon n naught plus 1, n naught plus 1 Then I can take my delta, sorry, y is equal to 1 upon n naught plus 1. Then what is the difference between x and y? This will be 1 upon n naught plus 1, that is still less than 1 upon n naught, and that is still less than delta. So, but for any 2 points satisfying this mold, so this implies 1 under root x minus under root sorry take this point, then x square minus y. What will happen? This will happen. So I am taking my, so you write this here, x dash, y dash, x dash and y dash are points from here, and their difference is less than delta. So I can take y dash is equal to this, x dash is equal to x square. So what is x dash minus y dash? That is this one. So what is difference of these 2 points is 1 upon this one. So by definition of uniform continuity, from here, equation number first you can say is, what you will have? You have their square root less than epsilon. So we have this one. So x square plus 1 upon n naught plus 1 less than epsilon. Okay, so it means x square plus 1 upon n naught plus 1 minus under root less than epsilon. Okay, but if I take n greater than equal to n naught, then what will happen? We have this x square plus 1 upon n minus x square will be less than equal to under root x square plus 1 upon n naught plus 1, that is less than epsilon. For all x belongs to minus 1 to 1, such that x plus 1 by n also belongs to minus 1 to 1. Okay. Now if I am taking this interval, x belongs to R, such that mod x is greater than equal to. So this is nothing but, okay. Now what about this? Under root x square plus 1 by n, 1 under root x square. So how can I can make it conjugate? So this will be 1 upon n x square plus 1 upon n plus under root. So I can take minimum 1 here. So it will be always less than equal to 1 upon n. So put here 1 plus x square plus x square. Okay. So there are positive quantity, no negative quantity. If I can skip x square, then it will be 1 upon less than. So I can always make it. So there will be, I can make it. So for large than, I can make it less than epsilon. For some existed, so I can choose, sorry, I can write it proper language. So by so choose n1 belongs to n such that 1 upon n1 is less than n. Then what we have? Under root x square plus 1 by n. Under root x square is less than epsilon for root and greater than equal to, and I am taking maximum of n1 into n2. That's n1 in n1 plus n0 plus 1. So this is a natural number and x belongs to R. So what does it mean? It means this function converges, sequence of function converges uniformly. X belongs to R. So this implies f1 under root x square plus 1 upon n converges to fx is equal to mod x uniformly on R. But you see that each function is differentiable. But this function is not differentiable. So we have also seen that a sequence of differentiable function can converge to a function, can converge to uniformly a function which is not differentiable. So if a sequence of function may converge to a function which is not differentiable, we have seen this example. So we want some theorem or result so that such problems do not occur. Okay, we have some conditions. Okay, so let's prove one result theorem. We want a condition under which if a function converges to pointwise or uniformly, then the limit function will also be a differentiable function. If given sequences of function of differentiable functions. Okay. So what is so throughout this lecture, throughout this theorem, I is an open interval. I is an open interval. Okay. So what is continuously differentiable function? let f I to r be a function, be a differentiable function. Be a differentiable function. Then f is said to be a, then f is said to be continuously differentiable on I if derivative function f dash is continuous on I. Okay. For example, I am taking this. So if you see this function fx is equal to x square, so it is, you take any open interval in R, this function is differentiable and its derivative is nothing but 2x. That is a continuous function. Okay. And this is differentiable function. So its derivative is also continuous. So it is a continuously function. So this implies f is continuously differentiable function. So what about this function? Okay. So this is continuously differentiable function. Now you see this function fx is equal to x square sine 1 upon x. If x is not equal to 0 and 0 if x is equal to 0. You see that this function is differentiable. Okay. Differentiable on R. But its derivative, what is that? Derivative function is this. What is derivative function? It is 0 if x is 0 and this is 2x sine 1 upon x and it is minus cos 1 upon x if x is not equal to 0. You see that this function is not continuous because limit at in the neighborhood of 0 does not exist. So this function is not continuous. Not continuous. So fx is equal to x square sine 1 upon x is not continuously differentiable on R. Okay. So we are going to prove a theorem now. let fn I to r be a sequence of continuously differentiable functions satisfying two conditions. First is that fn converges to f pointwise. Okay. Second one is fn dash derivative converges to some g function uniformly. Then f I to r is also continuously differentiable. And what happens? Its derivative is nothing but a g function. Okay, so let's see its proof. So choose x naught inside the interval. Okay, and put okay, then for any x belongs to I, x not equal to g x naught by fundamental theorem, by first fundamental theorem. There are two fundamental theorems. Okay, so by first fundamental theorem, we have what we have. So x naught to x derivative functions dx, what will have? Fn x minus Fn x naught. Okay, we have this. Let's say it equation number 1. Now Fn, since Fn converging to f pointwise, therefore what we have, because it is converging to pointwise, so Fn x will converge to fx and Fn x naught will converge to fx naught. Now Fn dash derivative function converges to g uniformly. And we know that if a function converges to uniformly, you take so it will converge to any closed interval in I, closed subinterval of I. So taking integration over that subinterval, that will also converge to, so what we got? We have limit x naught x fn dash will converge to x naught x g. It means limit is equal to this limit. It means limit n tending to infinity and tending to infinity, x naught x fn dash x dx is x naught x g x dx. Let's say it equation number 3. And what is equation number 2? Equation number 2, you say this. So what is the meaning of this? Limit and tending to infinity fn x is equal to fx. What is the meaning of this? Limit and tending to infinity fn x naught is equal to fx naught. So let's say it's equation number 4. So letting and tending to infinity in 1 and use 2, 3. We get, what we'll get? So if we will letting and tending to infinity, so in equation number, fn x will be replaced by fx, fn x naught will be replaced by fx naught, and this integration, because limit is tending, replaced by equation number 3. Okay, so what is we got? So f x minus fx naught is nothing but x naught gx dx. Okay, now see that since fn's are continuously differentiable functions, so each function is continuous, and we know that continuous functions, so these functions are continuous functions. Okay, and each fn is continuous function because fn is continuously differentiable. So continuous functions are Riemann integrable. So each function is Riemann integrable, and we know that if we sorry, each fn is each fn is each fn is continuous function, and if we know that if function is this is continuous function. So if we take integration, so this function is continuous function, and uniform limit of continuous function is continuous. So this implies g is also continuous. Each fn derivative is continuous function. Uniform limit of continuous function is continuous. So this is also continuous. And we know that if g is continuous, you take integration like this. The function which is defined, that is fx. You can bring this on right side. That is also differentiable. So this implies by second fundamental theorem that x naught x gx is differentiable on I. Okay. So this, let's say fx is equal to, this function is differentiable on I. Okay. And what is derivative of hx? And derivative of hx is nothing but gx. Okay. So let's say equation number 4. So this implies, so from 4 what we have? So from 4, fx is equal to hx plus fx naught. So this function is differentiable and this is constant function. So finally, f is differentiable on I. So now what is the differentiation of f, this is h dash x, and that is going to be 0. So this implies f dash x is equal to the derivative of hx. So it means f dash x is nothing but gx. So we have proved it. Okay. So what we have learned in this lecture, we have seen two examples. A function of contains differentiable function converges to pointwise to some function. Okay, but to converging pointwise to some function f, but f is not continuously differentiable. And second example, even if f and derivative converging to f uniformly, still f is not continuously differentiable. Okay, we have seen it. So we have proved a result in which condition we can, under some condition, this result can be have a suitable answer. Okay, so we have done this. So thank you very much for today's lecture. So kindly like, comment, and share, subscribe my YouTube channel. If you have any problem, you can comment on my YouTube channel. We will see you next class. Thank you very much.